So today we're going to talk about building ADTs using the TOSCA specification. It's an important skill. If you have questions about it, it's probably better that you ask them as we go on, just so that we're clear all along the way, because saving stuff for the end is going to be a lot of flipping back, and we're only 3 or so people. So I think we can do that quite easily. I've got Gab with me here, and I've got Greg as well. And I'll start this presentation here. If I can get it to click. Come on. I'm not going to talk any length of time about the TOSCA submitter, but I think it's important just so you realize why we write in TOSCA and where the TOSCA actually goes. So this might look scary, but all you need to know is that on the left, there's someone writing a TOSCA ADT, and it's going to pass through one component, which kind of has 2 different parts to it. So it's going to pass into the submitter, which is this box you see here, dotted box on your left, where it goes through a number of steps where it kind of gets translated into a format that we can work with. Then it gets passed to a number of different adapters, which are going to further translate it into something that each of our end components can really understand. So to make it much more simple than that, here's the information flow. There's a developer or someone writing a TOSCA, which is T, on the left side of your screen. They feed it into the submitter, and it gets broken down into understandable translations for the cloud orchestrator, which at the moment is Octopus, for the container orchestrator, which for the longest time has been Swarm, but we're now slowly thinking about moving to Kubernetes, and then to a policies engine, and to a security enforcer. So that's all I'm going to talk about for what actually happens in the submitter. Next thing we'll look at very, very briefly is what actually TOSCA is. It stands for the Topology and Orchestration Specification for Cloud Applications. It's developed by Oasis, which is a big standards group that deals with all things computing. We started off working with TOSCA Simple Profile in YAML, starting at version 1. Now they're almost all the way up to version 1.2. The good thing is, for the most part, nothing serious has changed. There's been no breaking changes introduced in any of these versions. So we're generally holding on to version 1, as that's the most supported. And we're taking kind of theoretical cues and hints from future versions, so that we're going to hopefully be remain kind of generic and remain compliant to TOSCA in the future. But for right now, all you need to know is that we're using TOSCA version 1. What is TOSCA? Well, it is a description of a language for defining application infrastructures that should exist in the cloud. What that more specifically means is that it defines all the components of an application that exist in the cloud for a particular deployment, and defines relationships between them. So the easiest ones are the kind of ones we certainly deal with most often. We have to define virtual machine components, container components, software or application itself. Sometimes we need to define networks, external volumes, and the list goes on. There's lots of things. Now we'll actually look, hopefully that was kind of a nice recap on what TOSCA is and what our submitter is. And we'll get right into it now, and we'll start to build an ADT using TOSCA. So here is, if you can actually believe it, for them missing a few key parts, but this is an overview of exactly what a perfect, ideal ADT should look like. So it has a number of sections to it. Obviously, there's things missing from each of these sections, but I just want to show you what it looks like and what we're going to get to. So TOSCA ADTs always start with this top line up here, TOSCA definitions version, and this is the version we're using. I mentioned 1.0 or 1_0 in this case, and they always start with that. And for MiCADO, they must start with that version, because currently that's the only version we support. So when you're first building an ADT, very simple, your first line is right there for you. The second thing that needs to happen that's also very important specifically for our ADTs is that we need to provide an import. So Gab and Greg and myself have taken to kind of creating a special subset of TOSCA, or a special kind of namespace of TOSCA that exists only for MiCADO. And within that namespace, we've defined, hopefully, all of the different components and properties and requirements that we think exist for anybody deploying an application to MiCADO. So it's very important, in order to benefit from the kind of abstraction and object-orientatedness of TOSCA, it's very important that we import all of these nice types, they're called, that we've created, and bring them in so that whoever's designing an ADT here can benefit from all those rich types that we've used. So the import line for that currently, you can see here, it's hosted in GitHub, and it probably will be for the foreseeable future. Right now, I've put a beta tag on this. That tends to be specific to the version. So if you're using MiCADO version 0.6.1, which is the latest Swarm release, in here, instead of beta, you will have 0.6.1. If you're deciding to be brave and use the Kubernetes version that's just been released, then instead of beta and instead of 0.6.1, you would have 0.7.0. So it's pretty logical, we hope. The next line is where we started getting into customizing the ADT for yourself or for your deployment. So whereas the imports line and the TOSCA definitions version have to be in every single one, here we can become a bit more flexible, and we try to tailor this ADT specifically for the app that we want to deploy. So here we have description, a topology for a CPU resource demo using MyApp. So this is just metadata. You don't have to put a description in. It's certainly helpful because anybody reading this in the future knows exactly what's happening, why this ADT was created, and maybe they'll be able to use it again. But again, it's just a string, it's metadata, it can be anything, it doesn't need to make sense, it's not going to be read by any of our components. The next bit is when we actually get into the more technical part of the ADT, is where we get into describing the different sections that make up the topology. And the key name for that, keep in mind this is all working in YAML. So if you don't have too much experience in YAML, it's certainly worthwhile. There's a website which I can link you after. It's called Learn X in Y Minutes, and it will teach you everything you need to know about YAML in about 10 minutes. YAML is a non-markup language, as they call it, or maybe it is yet another markup language. Nobody's really sure what it means. But it's a language which we can use, which is very, very human readable. It's based off of XML, I believe, and JSON types, but it's human readable, and it makes it easier for everybody to work with. So it's based off a very, very simple key and value setting. So you can see here all along since the top we've defined a key. For example, TOSCA definitions version is the key, and then we define a value, and the value is a string, which is TOSCA simple YAML 1_0. So the first key that we really need, and this is specific to TOSCA, so it needs to be exactly this, is topology template. And this starts off the section of this ADT, which will actually describe things very specific to the application that we want to deploy. Maybe eventually we'll want to destroy it.
Interesting for you.
Eventually we'll want to destroy it. The next key that we need to define, again, sorry, but we need to be quite specific here, is node_templates. And node templates, TOSCA refers to a node as any component of your application that will eventually be deployed. So if we go back a couple slides, The nodes are listed here in this small little list down here. So virtual machines, containers, pieces of software, networks, and volumes are all considered nodes by TOSCA. So in this node template section, we're going to be describing, quite simple, the virtual machines and the applications, or software or containers, or potentially a mix of all three, that make up the greater application that we're looking to deploy. You can see that the first node we're describing here is a worker node. Now here we get back a bit of flexibility. The keys, so the key names under node templates, so for example in this case worker_node, can be anything we like. That's us giving a name to the node. So I've called this one worker_node. That's fairly classic for most applications that have so far been deployed in MiCADO. We always call our virtual machines worker nodes. Then we can provide a description. Again, here we are with some metadata, so the description can be there. It doesn't need to be. It's certainly very helpful and it's very recommended. I've described it. This is a sample description of a virtual machine worker. I'm not being very creative, I'm sorry, but there you have it. The next thing we need to define, and this you'll need to think back a couple minutes when I said that Greg and Gab and myself have taken a substantial amount of time and have defined types or kind of abstract nodes that we think will be useful to anybody looking to deploy an application in MiCADO. And here we're referencing a very specific type. It's a type that we imported up in this line. So if we'd forgotten to import this line up here, we wouldn't be having this type to play with. We're very lucky we imported it, so we can now refer to this type. And the type is always going to begin tosca.nodes for any node types. For our nomenclature, we always have MiCADO as the first kind of hint there as to what we're using. Then we follow it with EC2 in this case. So this tells us that I'm looking to use AWS EC2, so that's the Amazon cloud. And at the end I put what it actually is, and it's a compute node. So that gives me my kind of base virtual machine worker. Obviously after that I'll define a number of properties that will relate to this node. I'm not going to talk about them right now because they're a bit more detailed and we'll get into it just after. So let's pretend we finished off our worker node. What's the next thing we need? Well, we have a virtual machine. Why don't we get a container/application to run on that virtual machine? So here we are again. Keep in mind, this is a key name that I can define however I want. I'm calling it my_app. But again, it can be any name you want to give it. A description, metadata, it can be anything. I've, again, been very boring here. And then finally, a type. So for any applications that we're deploying within Docker containers, and that's not making any reference to the orchestrator. I'm just saying if it's in a Docker container, no matter if it's being orchestrated by Swarm, or if it's being orchestrated by Kubernetes, or if it's being orchestrated by Mesos or another orchestrator that doesn't even exist yet. Every single Docker container that we want to define should have this type specifically. So it's a tosca.nodes.micado.container.application.docker. And once you get used to writing it out, it's pretty easy. We'll then define a set of properties that are specific to this application that we want to launch. Again, the properties aren't there. We'll talk a bit more about them later. And that's it. Those are the two nodes that we're defining. So this is a two-node topology. It is an application running on a virtual machine. Very, very simple, kind of the most basic approach we can take to creating a deployment in the cloud. Those are the two base necessities. So if you want an application running in the cloud, you need a VM, the virtual machine, and you need an application, obviously. So you can continue on in this. You could potentially define another few applications if you wanted to. So if you're doing a true microservice, you might have 5 or 6 different applications running in different containers that you needed to define. And you can go ahead and you can just keep adding them in under the node template section. Very, very simple. After we've defined the topology of our nodes, still within the topology template key, but now outside of the node template key, we want to define our policies. Policies are pretty important for us. They're a big part of why we think MiCADO is such a great piece of software, having these extensible, very kind of customizable auto-scaling policies that we like so much. So the policy section is an important place to define them. Now, the approach we take to policies is two-layered. We have both a policies section, you'll notice, which we're about to get into, and we have a policy types definition, which we're going to get to later. So the policies section up here is supposed to be very, very easy and very understandable for whoever's developing or writing this ADT. The policy types are a bit more specific, they're a bit more detailed, and they're generally going to come from, I think the idea is, policy developers or policy makers or policy creators. So people who are pretty in tune with different algorithms and different scaling algorithms and scaling logic, and they'll be able to write kind of the complex part of a policy. So what we're going to define now under this first policies heading is a very simple policy, which is based on a policy type defined further down. So our policies, so far we've only got one big one that we're really using. Very soon we're going to have some security policies. So I've typed here policies is my key name. Again, that's TOSCA. It needs to be policies. And then we specify the type of policy we're going to define here. So we create a list, and the way we create a list in YAML is with this little dash. And we say, okay, the first object of this array, or the first policy in this array, or the first policy in this list, is going to be a scalability policy. Again, scalability is kind of one of those TOSCA keywords, so it needs to be scalability. However, then we're going to go on and define within this policy, here's the type it is, and you can see we're abstracting here. So this is tosca.policies.scaling.micado.virtualmachine.cpu. So this is a very specific policy we're bringing in to this topology template for this deployment. And I can see it's a CPU scaling policy intended specifically for a virtual machine. So under this, so following this, we put in some targets. So which of the virtual machines we want this to target. And then we'd have some properties. And again, we'll get to that later. Under this, we might want to define another policy, one maybe for scaling.micado.container.cpu. And this would be very specifically for scaling containers. So you can see that list will go on, and that's our topology template done. We don't need to do anything else within the topology template section. We've got a worker node or a virtual machine. We've got an app that's planning to run on that worker node, and we've got a policy or a set of policies that are going to define how the app and the worker node scale in the cloud. The last thing we need to do, and we don't always need to do it because sometimes it'll be done for us, is we need to define the policy types. So in this case, we put them right here in the bottom, at the bottom of the ADT, just so it's very clear where they're coming from. Here, I'm defining a policy type, and I'm defining a policy type for container CPU scaling. So you'll see in the kind of bigger picture when I go a bit forward here, we've actually defined policy types for both container and virtual machine scaling. However, this is what a policy type definition looks like. We have to derive it from another policy that's been created at some time. So again, I mentioned we created a very kind of rich set of policies and types, as they're called, and we imported them again up here with this import line. And here's where we're actually using it again. So this tosca.policies.scaling.micado that we're deriving from is something that Gavin and Greg and myself have created and have put up in GitHub for anybody to use. Again, then we give it a description, and we give it some properties, and that's it. There's your Tosca ADT done. Let's now look at a couple different sections of this in more detail, and this is where, I guess I'll say now, before we start looking at too much stuff, because I realize it can be quite daunting looking at an ADT, looking at YAML and looking at weird things like this. and we don't want it to be. So it's really important to know that we kind of set out to create a number of very generic ADTs that we think are going to be usable in a lot of cases. And in order to use them, it should be pretty simple to just kind of copy and paste different sections of an ADT into whatever ADT, whatever application you're trying to deploy, and you'll get a good result from it. So everything has been created in such a generic way that we hope just by changing a couple properties here and there, you'll be able to run your virtual machine, your application with your specific policy needs. So the first thing we'll talk about and take a deep look at is the worker node. Here we have, as you can see, the worker node is coming in right under node templates there, so that's the section it falls into. It'll have the description and the type that we talked about earlier. We'll then need to define a bunch of properties for it. In the case of a virtual machine node, or a worker node in this case, the properties that we're defining are those that are needed to spawn up the VM. So we've taken a look at a couple different cloud orchestrators. We've looked at Octopus and Terraform so far, which both accomplish the same thing, and they both need a very, very similar set of data or of particulars to launch a VM. And they are, for the most part, an endpoint, a region name. This is obviously an example where we're just using Amazon EC2. If we're using a different cloud, some of these will change. But for Amazon, you need to provide an endpoint, you need to provide a region, you need to provide an image ID, and this is required across the board. So any cloud will require an image ID. You'll need an instance type, and you'll need a set of firewall or port openings, which are generally referred to as security groups or security group IDs. So all of the things in properties is what's going to get picked up by whatever orchestrator we're using, currently Octopus. Below properties, we have a section that you can see is called capabilities. This is a bit of an optional section, but I think it's very important to put into your ADTs, because imagine you are only looking at the properties section up here. If you're looking at this ADT and you're wondering, okay, well, they've got an image ID there, which is a bunch of digits. There's an instance type, which is T2 medium. I don't really know how big that is. You're kind of lost for what this node is actually defining. So that's why we have the capabilities section. It's for metadata. It's for human readability only, so it's not going to get read by any of our adapters or orchestrators. It's just so that whoever's reading this ADT can say, oh, okay, whoever's defined the properties up here, I know this image or this instance type gives me a 2 gigahertz and 2 gig virtual machine, and I know that this image ID up here, AMI 061, blah, 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 gives me an OS, which is Ubuntu Linux, and I can even see the version 1604. So great for anybody who ever wants to reuse this particular ADT on their own. Now, the last thing we need to do, and it's a very important part, when we're defining a node, is we need to tell it which orchestrator to use. And it's done very, very simply. We have a line called interfaces, which is, again, one of these TOSCA specific things that we need. And under interfaces, we just say which orchestrator we want to use. So Octopus is a MiCADO key name. It's something that we've created. And then we tell the orchestrator what we want it to do. We want it to create. And that's it. That node definition right there will get you a virtual machine up and running. We can take a bit of a closer look at it. I don't think it's too necessary there. So if anything was too small, I don't think so. You can see, boom, 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 3 sections really. A description of the virtual machine, the cloud properties, the cloud particulars that are going to get picked up to actually create this VM, and then a metadata section defining the resources so that they're readable by humans, and then lastly, describing the orchestrator. Now, say we wanted to use a different orchestrator, we can very easily do that just by changing the keyword Octopus to, say, Terraform, or something else that we've decided that MiCADO should support. And there it is again. That's how it looks when it's all done. I think it's pretty simple. The next thing we'll look at is a bit more in depth with the container itself. So this is the MyApp section we're on now. Again, it's going to look a little bit similar, not too dissimilar from what we just created with the virtual machine. We have the metadata section and the type specification up top. So that actually describes what this application is going to be. We then need to define what we're calling here the container runtime. And the container runtime, keep in mind there's a difference between Docker and Docker Swarm. So Docker is the container runtime. That's the actual container that exists on a virtual machine. Docker Swarm is a container orchestrator. So that decides how to deploy those containers in the cloud, or over a cluster at least. So here we're defining the container runtime, and every container runtime has some fairly generic properties that we've decided on. Two of them that we can see here, for example, are ports. So every container that is a Docker container will have some ports to potentially expose, and every container that is a Docker container has the ability to define an environment variable or a set of environment variables, and here's how we've decided to define those. So that's a fairly short list of properties at the top, and keep in mind they have nothing to do with orchestration. The next thing we need to define is the actual image that we're going to pull to create this, and the way that TOSCA likes us to do that is to create an artifacts section and define within the artifact section a name for your image. Here we've been very boring and we've just called it image. We give that a type. Again, here we are working with types. This is a TOSCA standard type for any Docker images, tosca.artifacts.deployment.image.container.docker. Then we provide it with a file name. So that's the name of it on whichever repository it's being hosted. This is an image for a stress ng. And then we specify the repository. So the classic repository is Docker Hub. That's the default one. That's the public one that Docker offers. However, if you were running your own private repository or private Docker registry, you would put it there. And you just provide a full URI or URL to it, and we would work it out. The last thing we need to do, keep in mind, up to this point here, we haven't even talked about whether we're using Swarm or Kubernetes. This is just a generic Docker container that is running the stress ng image here. So now we need to define which orchestrator is going to pick this up. Here you can see it's very, very similar to what we did in Octopus, or what we were doing with the cloud VMs. We define an interfaces section, and then we tell the interfaces section which orchestrator we want to use. So here we've said use Swarm. Do a create, because we're creating a container, or we're creating a set of containers, we're creating a deployment. And then implementation, here's the implementation we want you to use. So that points to the image. So we point to the image in implementation, and then we have an input section. Now the input section is Swarm specific. So this is going to, these are things that aren't specific, if you can believe it, to each and every single different orchestrator. These are things that we've decided are specific to Swarm and are potentially different in Kubernetes or Mesos or something else. So we've defined a number of things which are specific to the orchestration of this particular application. One of the best one is the deploy section here that you can see. This is how Swarm defines deployments. We can give it an initial number of replicas to begin with, so we've said 3. We can reserve some resources, so we can say, I want 1 full CPU to be available for each of these applications I'm setting. We can define a restart policy. So every time this container fails, wait 5 seconds and try and restart it again. And you have a max attempts of 3 there. So if you've ever kind of dabbled with Docker Swarm, or Docker Compose for that matter, you'll realize all of the input section is exactly conformant to the Docker Compose nomenclature. So we haven't done anything fancy here. We will let developers who are potentially familiar with the Docker Compose format or with Docker Swarm the ability to define properties just as they've done before. So everything gets defined laid out in a sort of dictionary or map format here. and that all gets passed on directly to the adapters and then directly to the orchestrator. So we can take a deeper look there, but I don't really think we need to. There's a description, there's the runtime properties, there's the container image, and then lastly, we describe the orchestrator. Now, just as before, what happens if we want to use another orchestrator, say Kubernetes? Very, very simple. We change the keyword here from swarm to Kubernetes. Then we still have a create key. The implementation points now to my image, which is potentially just another image that I've created, but is still a Docker image. And I've got then space to outline my inputs, which are not Docker Compose or Docker Swarm specific anymore, but are specific to Kubernetes manifest files. So anybody familiar with Kubernetes or writing Kubernetes YAML files will be familiar. This is the exact same nomenclature, the exact same levels we're dealing with everything. And again, it's a map. So very, very simple. We've defined actually all of the same properties as we defined on our Docker Swarm orchestration, and you can see the different keywords that Kubernetes and Swarm like to use. You can see there's a couple different differences in kind of where the levels begin, how far out the keys are, how nested everything is, and it's for that reason that we have this section, which is specific to an orchestrator. So that's the application done. There it is again, if you wanted to see it in full. And if there's no questions on either of the nodes that we've defined, we'll go and look at policies. Policies, we can get into, I think, certainly this section, so this higher level of policies, we'll get to policy types eventually, is, I think, very, very simple to understand because it works with such great abstraction. These are some of the best abstracted types that we use within an ADT, and you can see very, very simply, all that one needs to do when they're defining a policy is, again, we have this, we start this list under policies, and we say, okay, it's going to be a scalability policy. We then give metadata, just as we do with any of the nodes that we defined earlier. We give a description, and we give a type to it. Then we have a section which targets nodes above. So this target section is a list, as you can see, and it targets any nodes that we've defined up top here in our node template section. So you can see this is the scaling policy for VM CPU, so it only makes sense that it would target the worker node. After we've set a target, we have some properties. These are a number of, these are properties that are specific to the type of policy that we're extending here. So this is TOSCA policy scaling MiCADO virtual machine CPU. And within this virtual machine CPU type, I have a couple of constants. I have a couple of boundaries that should enforce this policy. And you can see that we've defined them here. So we have a node threshold max. That's the max CPU. 60%, we have a node threshold minimum. It's 25, so that's the lower boundary of CPU scaling. And then we have a minimum number of instances that MiCADO should maintain at all times. And we have a max number of instances that MiCADO should maintain, or that MiCADO should scale to, if necessary. You can see then we've defined a very, very similar looking policy just under, which defines the scaling policy for container CPU resource. Again, we give it a target. Here we're targeting the StressNG app, and you can see we've provided some properties which are specific to the tosca.policies.scaling.micado.container.cpu type. Again, those are min instances, so that's the minimum number of containers we want, and then thresholds similar as before. That's just a deeper look at it. Again, I don't think you really need it. And that's it. I mean, that's exactly how easy it is to define a policy. Obviously, there's a bit more depth to it, and that comes in the next and the last section here, the policy types section. So policy types defines all the logic and all the rules that are kind of hidden behind this policy, which looks so simple. And that's why I said this policy is often kind of written and tweaked by whoever's deploying the application. And this section, the policy type section, is going to be written by someone who's a bit more familiar with metrics, querying, scaling algorithms in general. So you can already see, you can first of all see what kind of a level we're at here. So the topology template was way up at the top. We had our node template section where we defined our VM and our app. We had our policies section, which we just finished. We just defined 2 scalability policies. And now you can already see, okay, this is looking a bit more complex than things we looked at before. Let's take a bit of a better look at it. Here we are. Policy types, they start off the same as any other node or policy or pretty much anything else that's defined in TOSCA. We provide a description for it, and we provide a type for it. Now, the only difference is here we're not providing an explicit type, we're deriving from a type. So you can see derived from, this is deriving from one of those rich policies that we've created and that are kept up in the types file in GitHub, tosca.policies.scaling.micado. And we're going to go ahead and we're going to extend that with some, in this case, alerts and rules, which are going to define the scaling of the application that we've just gone and done. So this is a real kind of copy paster here. This can be taken from a stress-ng application, which uses, which relies on CPU resource to scale, and it can be transferred to pretty much any other CPU scaling application. So any other application that needs the ability to scale CPU, they can literally copy and paste this word for word, and it will work perfectly, assuming that they define here earlier in the policy section a new target for it, and then whatever specific needs they have. So whatever thresholds they want to work with, and whatever minimum and maximum number of instances they want to work with. So don't be too put off by it. But I will kind of explain it to you and go over just quickly the scaling logic here. So here we define 2 things. The first thing we define are a number of alerts. These are alerts based on a component called Alert Manager, which is closely tied to Prometheus. Prometheus is our metrics manager or our metrics capture software or application. And these alerts will be generated based on the information in this expression here. So what the expression is doing is it's finding the average CPU usage of, in this case, the container CPU, and it's saying, okay, if this is over the node threshold, CPU threshold here, node threshold max of 60 that we defined earlier in a more generic fashion, then raise this alert, raise the service overloaded alert. And it says if that goes on for more than 30 seconds, then it's time to raise the alert. Second, you can see we've done a very similar thing. Here, it's the average rate of computer CPU usage under the lower node threshold of, I think it was 25. Again, if it's under that for 30 seconds, raise a service underloaded alert. So that's all that the alert section does. The scaling rules section says, okay, if, and this is all in kind of Python code, so if you're not too familiar with Python, again, it's going to look a bit bizarre to you. But it's saying, okay, if I get a service overloaded alert, here's what I want you to do. I want you to up the container count by 1. If I get a service underloaded alert, I want you to reduce the container count by 1. And that's the logic behind it. So again, it's not too important because not everybody writing ADTs are going to be writing policies each time they do it. Certainly, I would say most people writing ADTs will be finding policies that have already been created, and they'll be extending them with their specific needs, as we've just seen here. So we don't really need to look at this, I don't think. It's very, very similar, only for the VM. But as you can see, it works pretty much the same. It looks at the overall node CPU instead of just looking at the container CPU, generates an alert if it's over a certain threshold, generates an alert if it's under a certain threshold, and then you can see the scaling logic down here in the scaling rule. If the node is overloaded, bring the node count up by 1. If the node is underloaded, bring the node count down by 1. And that's it. So very, very simple. It looks daunting, I'll admit. That's the policies type section. It's certainly the biggest section we've seen so far. This can be abstracted. So this whole policies type section can be abstracted right out of the entire topology, and I could just import it if I wanted to. So if you remember back to a very kind of early slide that we had there, where we had this import section up at the top here, I could add a line. This is just a list, so I can add another line to it, and I could have all of these policy types, all of these rich policy types down here, defined in another file, kept somewhere in GitHub that I can simply point to and have it brought down into my ADT. The user still defines policies in the exact same way at this upper level within the topology template, and they don't even know that there's a policies type. So that can be abstracted away. That's basically it. There's our repository is currently here. So kept at github.com, MiCADOscale/TOSCA. Again, there's so much potential for kind of copy and pasting here, and I know nobody likes to hear copy pasting, but it's the only logical way to really build. I think it's certainly the fastest way to build any ADT, and TOSCA is meant to be generic. It exists for exactly this purpose, so that we can take nodes that we've defined before, and we can simply move them around and use them again. TOSCA is supposed to be reusable, so it was created to be copy and pasted, basically. I think that's it. I've got a couple slides on another policy here. Again, this doesn't necessarily need to be shown, but I can certainly send these slides out after, and you can kind of see a different type here. So this particular policy is not using alerts at all. It's simply scaling based off an external metric that is pulling in, and this is the way to do that. I don't know if you want me to spend any time on that. I don't think it's necessary. That's it. Hopefully there's lots of questions to go around. Got what, 15 minutes there left. Do you two have any input? No? Okay. Does anybody, Ben or Andreas?
Yes, I would like to ask for other methods than CPU-based scaling. Is there anything available at the moment?
Yes. So there is. Okay, good. I thought that's exactly why I put this in here, really, because I thought someone would be interested to see it. So here is. Let me just swap this. Here is a policy definition. So remember, there's those two types of, there's a policy, and then there's the policy type itself. So this is a policy which is scaling not based on CPU. So it's different from the last policy in two ways. The first way is it's not scaling based on CPU. It is scaling based on any external metric that Prometheus can capture. So Prometheus is our metrics manager I mentioned. You can extend Prometheus with these things called exporters. And people have already written exporters for a number of different pieces of software and applications. They've written them for all the different databases that exist in the world. They've written them for most of the HTTP servers that exist in the world. And they're writing them for pretty much any application which generates some data, which should be captured as a metric and measured. Prometheus can be configured to get that information. So that's the first way it's different. The second way it's different is it doesn't generate alerts. So this uses the metrics captured and makes scaling decisions based on those, rather than creating alerts and then making scaling decisions based on alerts. So it's different in two ways. This is, I've called it virtual machine external metric. The way I'm using this policy is I set up an HTTP server using Nginx. So just a very simple web page, let's say. And I use Prometheus along with the Nginx exporter, which I'm defining here as a source. I use it to capture the number of HTTP requests per minute. And I then define a metric max. So a maximum number of requests that I would like to see, and I have a minimum number of requests, and these are going to be the things that influence my scaling. Just as before, I've defined some minimum number and maximum number of instances, and then I've done the same. That was my virtual machine. I've done the same for a container. So the logic of it then makes a query to get the HTTP requests and to get the rate over 3 minutes here, and then within the scaling rule, I make some decisions based on how many requests are coming in. So generally, I scale up to support the number of requests coming in automatically. I don't wait for any alerts, though. So it's if I'm getting a lot of requests in, I'm going to scale straight up. And if requests aren't coming in so much, I'm going to scale right down. So it's a very quick HTTP request scaling, and it uses an external exporter to get all those requests into Prometheus so that I can use them as a part of my policies. So there's that one. There's one more that we're currently using, or kind of two actually, and they're both queue-based policies. So I don't have either of the examples here, I'm sorry, but I can give them to you. I can get them to you. One's already in the Ansible playbook under CQ. You might have seen it. It's one of the tutorials. And the queue policies, they read, basically there's an external server running somewhere that is kind of, that is a queue. So there's a number of jobs waiting to be completed on this external server, and MiCADO starts and spawns up a number of workers to capture jobs from the external server and complete them. And so the policy is based on the length of the queue on the external server, and then that policy instructs, we then provided a deadline, so these are deadline-based policies. We then provided a deadline and say, okay, I need to finish all those jobs in the queue in the next 5 minutes. And the policy will adjust the scale of our application so that all of the jobs up there will finish in the required amount of time. So those are the three different policies I can think of. There's CPU-based, which is really actually resource-based. So it could be CPU, it could just as easily be memory or bytes transmitted over the network. Any resource we can measure very, very easily. There's then an external metric, not using alerts. So we're measuring HTTP requests to an HTTP server. And then there's the deadline-based queue policies. So there's those three so far. And we're, I guess, always looking for more.